Good afternoon, children. Welcome back to the next lecture of section 9.1 vector functions. So before beginning this session, I would to make a point, that is, many of you informed me that it is difficult for you people to graph a particular given vector function. So we'll deal with it. I'll upload a session related to the same in your Google Classroom. You guys can check it. So let us begin the second lecture. So we are going to discuss about the limit, continuity and derivatives of a vector function. Now we are familiar with these words, limit, continuity and derivative, in previous class, because we have learned it in the previous semester. But the difference is that there we were dealing with just basic functions. Here we are extending it to a vector function. So the notation of limit of a vector function r of t equal to vector f of t, g of t, h of t is defined in terms of the limits of the component functions. The mathematical definition is given as follows. If limit t tends to a, f of t, limit t tends to a, g of t, and limit t tends to a, h of t exist, then limit t tends to a, r of t equal to the vector limit t tends to a, f of t, comma limit t tends to a, g of t, comma limit t tends to a, h of t. So what is the definition of limit? To find the limit of a particular vector function, it is enough to find the limit of the components functions which are present in that particular vector function. So for a limit of a vector function to exist, we must note that the individual limits of the component functions must also exist. Now the notation t tends to a in the given definition can be replaced by t tends to a plus, t tends to a minus, t tends to infinity, or t tends to minus infinity. All these terms have the meaning which you all have learned before itself. Now next is a theorem 9.1.1. It gives us the properties of the limits. So the theorem states that if limit t tends to a, r1 of t equal to l1, and limit t tends to a, r2 of t equal to l2, then we have three properties. The first one is limit t tends to a, c into r1 of t is equal to c into l1, where c is a scalar. Second one, limit t tends to a, r1 of t plus r2 of t equal to l1 plus l2. And third one, limit t tends to a, r1 of t into r2 of t is equal to l1 into l2. Now that we have defined what is the limit of a vector function, we can move on to the definition of continuity of a vector function. A vector function r is said to be continuous at a point t equal to a if it satisfies the three properties. First one, r of a must be defined. Second one, limit t tends to a, r of t must exist. And the third one, limit t tends to a, r of t must be equal to r of a. So this is the definition of continuity of a vector function. Or we can say that a vector function is continuous at a point t equal to a if and only if the corresponding component functions f, g and h are continuous at that particular point. So now if we think about limit and continuity, both are same as we have discussed, as we have studied earlier. The only difference is that we have to consider the component functions of the vector functions. If the limit of a component functions of a vector function exists, then the limit of that vector function will also exist. Similarly, if the component functions of a vector functions are continuous, then the corresponding vector function will also be continuous. Now after continuity, we have the derivative of a vector function. Now the derivative of a vector function r is given by r dash of t equal to limit delta t tends to 0, 1 by delta t into r of t plus delta t minus r of t for all t for which the limit exists. So this is the definition of the derivative of a vector function. Now also note that we can denote the derivative of a vector function r using dr by dt also instead of r dash of t. Now next is the theorem 9.1.2. It gives us the idea of the derivative of a vector function. Now we have already seen the definition of the derivative of the vector function. Now go to the theorem 9.1.2, that is, if r of t, the vector function r of t equal to f of t, g of t and h of t, and suppose the derivatives of each these components exist, then we can say that the theorem states that r dash of t, that is the derivative of the vector function, will be precisely vector f dash of t, vector g dash of t and h dash of t. That is, r dash of t would be the vector f dash of t, g dash of t, h dash of t. Now let's go to the proof. The proof is pretty much simple. We know by definition r dash of t will be equal to limit delta t tends to 0 1 by delta t into the vector f of t plus delta t, g of t plus delta t, h of t plus delta t minus the vector f of t, g of t and h of t. Now taking delta t inside, we get limit delta t tends to 0 into, and using vector operation we have f of t plus delta t minus f of t by delta t, comma vector g of t plus delta t minus g of t by delta t, comma h of t plus delta t minus h of t by delta t. Now when we apply the limit inside, we get r dash of t will be equal to the vector limit delta t tends to 0 f of t plus delta t minus f of t by delta t, comma limit delta t tends to 0 g of t plus delta t minus g of t by delta t, comma limit delta t tends to 0 h of t plus delta t minus h of t by delta t. Now what are these? These are basically f dash of t, g dash of t and h dash of t. That is f dash of t, comma g dash of t, comma h dash of t. So the proof is very simple. We have shown that the derivative of a particular vector must be the derivative of each of its component. Now next we'll move on to the definition of smooth curves. When the component functions of a vector function r have continuous first derivatives and r dash of t is non-zero for all t in the open interval a comma b, then R is said to be a smooth function, and the curve traced by that function is called the smooth curve. So what is the condition for a smooth function? The condition is that the vector function R of t must be continuous and it should have non-zero derivative for all t in the open interval ab. Then we say that a function will be smooth and the graph corresponding to that particular function will be called the smooth curve. So with this we will conclude today's session. So let us come to a brief summary of the session. What we learned in this lecture, we discussed about the limit, continuity and derivatives of a vector function. The thing to be noted is that we are all familiar with these terminologies. The only thing is that we have extended it to the vector function. So for a vector function to be continuous, the corresponding component functions must be continuous, and for the derivative to exist, the components or component functions must also have their derivatives and correspondingly, and we also defined what is meant by a smooth curve. So thank you, stay home, stay safe.